All right, so we're going to now talk about 8.5, the section 8.5 and the section 8.5. We're going to do this in 4 separate parts. It's quite an extensive section, as a matter of fact, and that's why I have given you guys the packet that you guys should have been able to download from the LMS section. Now, so we're talking about applications in, so what kind of in science, basically, mostly in science, right? So one of the things that we're talking about is work, okay? So work is equal to force times distance, and we know that, right? Force is what? Force is basically, what we're mostly going to talk about is weight. So force is weight here. So weight is calculated by mass times g, right? Which is basically the gravitational acceleration. So we're going to have mass times g. So mass is what? Mass is a unit of what is there, right? So mass in your SI units would be what? It would be kilograms, right? And in the British unit, mass would be pounds mass, or for those of you who understand, there's slugs, okay? Slugs, you're not going to have to worry about too much about pound mass, right? Okay? Whereas the gravitational constant is going to be 32 feet per second squared, or 9.8 meters per second squared. Again, depending on whether you're using the British unit or you're using the SI units, okay? So that's weight, okay? So, and force is this. Now this works as long as this guy here is constant. If this guy here is constant, no problem. We can do it this way. If it's not constant, right? If it's not constant, so in other words, if you have something like this and you have a weight, right? If you have a weight that is a certain amount of forces. So what? Okay, so let's go back to the force. Force is mass times this, right? So the unit for force is going to be what? Kilogram times meter squared per squared, right? Second squared, I mean meter per second squared, right? And this is going to be kilogram meters per second squared, what we call a Newton, right? So in the SI units, the force is going to be in newtons. And in the British unit, you're going to have what? You're going to have pounds force times feet, okay? So we call it, actually, generally it's called the foot-pound force, okay? Foot-pound force, okay? So foot-pound force, all right? So let's say I have a force here of, I don't know, 100 newtons. I have 100 newtons here, right? 100 newtons. I'm going to move that 5 meters, okay? So I'm going to have what? Now I'm going to have 500, so I'm going to have, the work is going to be, well, work is going to be 100 Newton times 5 meters, which is 500 Newton meters. And Newton meters is a joule, right? So you're going to have 500 joules, okay? All right? And this is how it works if the force was constant, okay? If the force is not constant, what do we have? So basically you have a what? You basically have an area under the curve, correct? Area under the curve, where you have force on one and direction or distance on the other one, right? So force and distance, okay? So if they are not constant, then you basically are forced to do something like this. It's going to be f of x dx. Okay? In other words, since f of f is not constant, it is a function of distance, right? It would be f of x times the distance. I'm sorry, not the distance. F of x dx. The distance is from A to B, correct? A to B. So your force is going to look like this. us from f of x, a to d, so it's area under the curve, like that. Okay? So let's do example number 1. Example number 1 says, find the work done by the force F equal to cosine pi x newtons along the x-axis from 0 to 1.5 meters. So I'm going to go from, so f of x, okay, f of x is equal to cosine pi x, and we're going from 0 to 1/2. So 0 to 1/2 cosine pi x dx, right? So this would be what? Pi over 1 sine pi x evaluated from 0 to 1/2, right? So what do I get? I put 1/2 in here, this becomes 1 over pi. When I put 0 in here, this is 0, so your answer is 1 over pi, it looks like. Yep. All right. And the unit here would be what? Since this was in newtons, this was in newtons, and this was this in meters, Newton meters was going to be a joule, correct? All right, so that's that. Let's go to example number 2. Example number 2, you have a kind of an interesting thing here. All right, an interesting thing. Example number 2, you are lifting a bucket. So you're lifting, you have a pulley here, and you are lifting a bucket here, and you're pulling on this, you're lifting the bucket from the ground. Okay, so, and, well, from the ground, let's say the ground's here, right? Let's say the ground's here, and you're lifting a bucket. Okay, except for this bucket has a hole in it, and it's leaking water as you bring it up, okay? And you're bringing it up for from 20 meters. So this guy here is 20 meters. You lift it up, and it leaks. So it's a leaky bucket weighs 22 newtons empty. Okay, so it's the bucket itself is 22 newtons, and it is lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 0.4 newtons per meter. So the rope is 0.4 newtons per meter. The bucket was 22 newtons. And it starts with 70 newtons of water, but at least at a constant rate to finish it. And it drains, just finishes draining as the bucket reaches the top. Find the amount of work done by A, lifting the bucket alone. The bucket alone, okay? So the bucket is 22 newtons, but it never changes. It's always going to be 22 newtons. So I'm going to go, my work done is going to be 0 to 22 newtons dx, right? So that's going to be 22x, 0 to 100, 440 newtons. Okay, that was pretty simple. B, lifting the water alone. The water starts at 70 newtons. Okay, the water starts at 70 newtons. So it starts at 70 newtons. And then by the time I am done raising it at 20 meter point, I have no water left. Okay, so the function for this guy is what? I have to find this line, right? I have to find this line, right? So I'm going to be what? The f of x, the line is going to be, right? Starts at 70, right? And it's going to drain out, right? But it's going to drain out at a rate of what? Rise over run, right? Rise. So rise would be 70. 70 is going to be, but it's going down, negative 70 overrun. All right? So that's going to be your formula for that, right? So I'm going to have W work is 0 to 20, negative 7 over 2x plus 70 dx, negative 7 over 4x squared plus 70x, evaluated from 0 to 20, right? If I do that, there's going to be 400 divided by 4 is 100, so minus 700, right? And then I put 20 here, I get 1400. I put 0 and they both go to 0. 700 newtons, right? So 700 newtons, okay? 700 newtons. 700, 700 joules, I'm sorry, 700 joules. This is joules also here. These are joules, 700 joules. Okay? So C. C is what? C, they asked for lifting the rope alone. The rope alone is what? The rope alone was started at, what does it say? 0.4. Okay, so at 20 meters, how much rope do I have? At 20 meters, I have, this times 20, right? So it's 8 newtons. I have 8 newtons of rope. So I'm going to have, it's going to be the same thing here, because by the time I'm done all the way to the top, I'll have no rope left, right? So I'm going to start at 8 newtons here, right? And this is going to be 20, okay? So let's do something different here on this one, since we're kind of running out of space too. I'm trying to find the area of the curve. Well, it's nothing more than the area of the triangle, right? So it's going to be 8 times 20, which is 160, divided by 2, which is going to be 80 joules, okay? So C would be 80 joules. Basically, it's the area under the curve here. The height is 8. The base is 20. So 8 times 20 divided by 2 is 80 joules. Okay. And then D. Lifting the bucket, water, and rope together would be nothing more than just adding this guy to this guy to this guy. So we're going to have 1140 plus 80. So it looks like 1220 joules. 1220 joules, yes. Okay, so we'll stop here today.